My name is Haley and I'm going to be presenting our research simulating inter-observer variability across clinical experience levels for brain tumor segmentation on behalf of me and my co-authors. When looking at segmentation tasks in medical imaging, manual segmentations are subject to variability due to inherent human biases. These differences in segmentation styles can introduce inter-observer variability and may be impacted by a wide variety of factors. When these manually annotated segmentations are then used as training data for deep learning segmentation models, there's a risk that these models may learn the labeling styles of a specific annotator and introduce what we refer to here as annotator bias. One solution to combat this problem is to combine multiple manual segmentations of the same region. Now, while this may be a reasonable solution in some instances, these solutions aren't proven to be robust in practice. Additionally, manual segmentation tasks are tedious, time-consuming, and resource-intensive. Another barrier to having more approaches in which we can mitigate this annotator bias is that it's often difficult for us to get datasets with multiple segmentation masks, as most often the available datasets only contain a single ground truth mask. And so the difficulty here is that this ground truth mask may represent a combination of various annotator styles or perhaps a single annotator style, and this makes it difficult for us to assess if the annotator bias is being learned in the deep learning model. So our research aims to address this by investigating a method in which we can analyze these biases without having to access these multiple segmentations. So for this, we developed two specific aims. Our first is to simulate those inter-observer differences from a single ground truth, and then our second was to use these simulated differences in a case study in order to assess if this is being learned by deep learning models, as well as if that's affecting model performance. So in our simulation, we modeled inter-observer differences off of a study which reported segmentation variability among 3 radiologists, including different experience levels. Specifically, we used the reported relative volume metric to simulate over and under segmentation patterns, which we achieved using morphological operations. Spatial differences were modeled using mean center of mass differences and were introduced by modifying the shape of the morphological kernel. We then applied both of these changes to a ground truth segmentation mask in order to create our 3 simulated observer profiles. For our case study, we used 1,000 patients from the Bratt's meningioma dataset as our ground truth labels. Once we simulated our 3 observers across 1,000 patients, we then assessed inter-observer variability using the dissimilarity coefficient as well as a common agreement heat map. To assess model performance, we trained 4 models. The first 3 models were trained using each simulated observer segmentation, and the 4th model was trained using all 3 of the simulated observer segmentations. We then evaluated model performance using DICE and HD95 metrics, which we validated against both the Bratt's ground truth labels as well as each own observer-specific label. So here are the results of our simulation on the Bratt's dataset. And this is the common agreement heat map between these 3 observers. Additionally, these are the DICE agreement scores between the observers as well as against the ground truth, and we can see that our simulated observers showed a wide range of agreement between each other. So in terms of model performance, our first model performed higher on the DICE score against their own observer-specific segmentations than against the ground truth segmentations. And so this is indicating that the model is learning these observer-specific preferences and therefore the annotator biases. Models 2 through 4 don't show the same pattern in terms of DICE score. They do perform better on the ground truth data. However, the HD95 values are still quite high, and so this indicates that while overall location annotator biases aren't being learned in these models, the specific boundary delineation annotator preferences are being learned. Additionally, models 1 and 3 show similar performance in HD95 values against each observer-specific segmentation, but when we look at the ground truth segmentations, we see that there's a bigger gap here, and this indicates the risk of using these model performance metrics if only one ground truth segmentation is available for validation. So in conclusion, the models are learning these observer-specific biases, and these metrics may not be reliable measures if we only have a single ground truth segmentation available. These annotator biases may negatively affect the model performance and therefore undermine the fairness, trust, and transparency of the models. Our study does have some limitations, so our simulation is only based off of one study. As well, our simulation framework does not yet account for variability occurring from other human factors, for example, clinical specialties. Thank you so much for watching. I'm happy to answer any questions if you just reach out to me by my email here.